For this video, let's try to show the proof for the identity, or specifically Pythagorean identity for our given hyperbolic functions. But this time, it's actually a subtraction here, or 1 minus the square of the hyperbolic function tangent z, which is equivalent to the square of the hyperbolic function of secant z. Now, let's not forget that if we talk about a certain angle in real numbers, we have 1 plus the square of tangent theta is actually equivalent to the square of secant theta. Similarly, when we talk about the trigonometric functions before these hyperbolic functions here, we're also able to identify that if we have 1 plus the square of the tangent z, it's still equivalent to the square of secant z. But when we talk about hyperbolic function, we have here the difference. So that's where it is different from the trigonometric functions of complex numbers. Before we can dig to that, let's not forget the forms for the hyperbolic function of tangent and secant. For the hyperbolic function, or the square, just for the tangent first, the hyperbolic function of tangent is actually the ratio of our the function, the sine, hyperbolic function for sine and hyperbolic function for cosine. Okay, so it's actually it's in this form. You will have e to the power of that's positive z minus e to the power of negative z all over e to the power of z plus e to the power of negative z. That's for the hyperbolic function of tangent z. Okay, for secant, it's actually the reciprocal of your hyperbolic function of cosine z. It's equivalent to this form. It's 2 over e to the power of z plus e to the power of negative z. Now, for this 2, we're going to use them to prove our given identity here. So again, we will start, but we are going to subject them into squares, as these are actually indicated in our identity. But either way, let's start with the left hand side. 1 minus the square of the hyperbolic function of tangent z, which is written, or can be written as 1 minus in this form. Okay, the square is outside, so that we can just simply plug that in here, and again, our target is actually this one, but since it's square, it's also formed into that one. It should be a square. That's our target here. So basically, we know our target, so let's start with our goal, and of course, hopefully we could manipulate this carefully. So you have here 1 minus your tangent is e to the power of z minus e to the power of minus z, all over e to the power of z plus e to the power of negative z. You're going to square that for your tangent. So let's square first our numerator, or distribute that using power law. Share that to this binomial and this binomial as well. So we have here 1 minus e to the power of z minus e to the power of negative z. You're going to square that over, you have e to the power of z plus e to the power of negative z, squaring that as well. Now for this, let's try to manipulate or expand only our numerator. Why are we not going to simplify this? Because looking at this perspective, take that our goal is secant squared. That would mean if we're going to look at the square of your hyperbolic function of your secant, it would be in this form, 2 over the square of this. Okay? If we're going to apply the power law, it's actually just equivalent to 4 over the square of your denominator. Now for this, it's already equivalent to this form. Okay? So let's just take it at what it is in the meantime. Okay? Because if we're going to expand that later on, we're still going to factor that to meet this standard. Okay? However, what we can do here is, of course, what they call this one, combine the two fractions or rational expression. We know this to be over 1. So what we have here is the same denominator, e to the power of z plus e to the power of negative z. You're going to square that. But what will happen here is when you divide it to 1 and times the exponent, or the numerator, you will have your e to the power of z plus e to the power of negative z, the square of that. At that time, you can actually expand the numerator, not just the denominator. You're going to expand the numerator because it is paired with minus e to the power of z minus e to the power of negative z. You're squaring that as well, right? Okay? So we're going to expand both terms on the numerator, not the denominator, because again, it fits the standard here. Now, you can actually apply here if you're thinking deeper concepts of squares. You can actually use here the difference of two squares, difference two squares. Okay, but allow me to use the general method of expanding them, okay, to just also illustrate some relationships of exponents as well. But of course, you can, as mentioned, you can always try to use here difference of two squares. This time, you will have here the square of the first term plus twice the product of the first term and the second term plus the square of the second term for the first group minus, take note of the grouping, let's have the grouping here, the square of the first term minus twice the first term, the second term, plus the square of your second term. Okay? Take note that we group the second group because we are going to distribute the negative sign later to all of the terms. All over the same denominator here. Again, we did not expand that because we already had our target. So with this, you have e to the power of 2z. Take note of what will happen here. That's z minus z, addition of exponents, because that's on product rule. So you will have here plus 2 e to the power of 0 plus e to the power of negative 2z. On the second group, minus still e to the power of 2z minus 2 e to the power of 0. Again, that's 0 plus e to the power of negative 2z. All over, you will have here e to the power of z plus e to the power of negative z. You're squaring that. This time, let's try to make it 1 as well, and remove the grouping symbol by distributing the negative sign all the terms of the second group. So e to the power of 2z plus 2 plus e to the power of negative 2z minus e to the power of 2z. This minus becomes plus 2. This plus becomes minus e to the power of negative 2z. Again, as we try to distribute the negative sign all over the square of your denominator. This time, let's try to look at the terms of a numerator. We have here the positive e to the power of 2z and the negative of that. So basically, that's actually 0. Here, and the opposite of that as well. So you will have also 0. So we will have 2 plus 2. Okay? So you will have here 4 over your denominator still as it is. Now, when you look into this form, it's actually already this form here, our goal, which could be written in this form, and that's actually the square of the hyperbolic function of second z. So, you can write it in this manner, right? 2 over e to the power of z plus e to the power of negative z, you're going to square that, would be equivalent to the square of the hyperbolic function of second z. And this time, we have shown that this is true when we started with the difference of 1 and the square of the hyperbolic function of tangent z, the goal for this video. So as mentioned, in our real numbers and the complex numbers for trigonometric function, the pluses are true. But for hyperbolic function, you have here minus. Thank you very much for watching.